I don't really want to go over conservation momentum, but I'm going to do it really quickly. I want to make a model and show you how this works. So let's just go over the big ideas for, and this is the simplest collision you can ever see. We're going to model it. It's going to be awesome. You're going to be surprised. You will be surprised at how much cool stuff we can get out of this. So this is the momentum principle. This says that the total force on an object is equal to its rate of change in momentum, and momentum is mass times velocity. So now imagine that we have two interacting objects, like this. So A and B, and they're moving toward each other. They both have a momentum, PA1 before the collision, PB1 before the collision, and they collide. During the collision, this is B, and that's A. So there's a force, FB, pushing on A. And then A pushes back, FA on B. But the thing is, we have the momentum principle. We also have this idea that forces come in pairs. So actually, FB on A is equal to negative FA on B. Forces come in pairs. You may call this Newton's third law, and that's fine. Just don't say for every action there is an equal and opposite reaction, because I just don't like that. You can say it, and I'm not even going to hear you, but don't do it. Just don't tell me you said it, okay? Because action and reaction imply forces are, implies conservation momentum, but this is actually more than that, right? Because if I just have two objects pushing, if I push on a wall and then we're not moving, it's kind of hard to say action. I don't want to talk about that right now. I want to make some Python stuff. So if that's true, and I look at object A, I can say, the change in momentum of object A with respect to time is going to be the force. If that's the only force acting on it, it's this, FB on A, which is equal to negative the change in momentum of B with respect to the time, which is equal to negative of negative FB on A. Right. So since they're both equal to opposite forces, their changes in momentum have to be equal and opposite. Or you can say delta PA plus delta PB, and the times are the same, is equal to 0. Right. Or the total momentum before is equal to the total momentum afterwards. This is conservation momentum. Conservation of P. I'll just put it. Now, this is true if the only forces are internal forces, right? If there's a rocket acting on this one, that doesn't happen. It's not true anymore. But we can make a collision where this is true. So we're going to make a collision. And the key to conservation momentum is that you have some force between the two. We can make a really great force, but I'm going to make a silly force. So let's say have object A right here and object B. And I'm going to calculate the vector from A to B, and I'm going to call that the vector R. Okay, so these could be anywhere. So that's RA. That's RB. And this is a lot like gravity, but it's not gravity. And so R is going to be RB minus RA. So that if I know the vector locations of these two, I can find the vector between them. Now, let's say the force on B, FB, is going to be a repulsive force, right? I want them to repel. So FB is going to be some constant, let's call it B times, I'm going to write it, I'm making up a force on the fly. B R hat over R cubed. And you may think, what the heck are you doing? I don't know. I don't know what I'm doing. Okay, so we know that B has to have some properties. Let's just say, I'm going to put B as 1, and that would be in units of newtons per meters cubed. And so what I'm going to do is I'm going to find this vector R. I'm going to take the magnitude and cube it, and then I'm going to find the unit vector R so that I can find the direction of the force FA on B. And then I can find the force FB on A because it's just the opposite. And then what I can do is to calculate that force on each of these and assume it's constant over a short time interval and update the momentum and then just let the whole thing play out. I'm doing it this way because I want it to be a very short range force, right? Because if R is very large, the force is pretty small. But in general, what we're going to do is, let's say delta t is 0.01. So if I look at object A, I can say the net force, F net, which is this force, the opposite of it, is delta PA, delta t, and that's going to be equal to PA2 minus PA1 over delta t. I can solve this for PA2. PA2 is equal to PA1 plus F net, which I'm going to calculate, F net A delta t. So at the end of the time interval, I can find the new momentum. Now I can say V average is delta R A over delta t. And let's say that's equal to PA2 over M2. That has a mass, right? Mass, the momentum divided by the mass. So if I do the same thing and call this RA2 and RA1, I get RA2. I'm skipping over this because I want to get to the Python. RA1 plus PA2 over M2 delta t. And then I do the same for B. So what I'm going to do is to calculate this vector. I'm going to use that to calculate the force. I'm going to use that force to update the momentum, update the position for both of the objects, and then do it again. Okay. And since they have equal and opposite forces on them, the momentum should be conserved. So I'm going to pick a mass. Let's pick some stuff here. Let's say PB0. It starts at rest, 0, 0, 0, and kilogram meters per second. And let's give them both a mass. Let's say MA is 0.1, MB is 0.3 kilograms. And then I'm going to give this one an initial velocity of, let's say, 0.2 meters per second that way. And I'll fix all that. And let's just let it ride and see what happens. Kind of excited. I'm thinking about these as like tennis balls, so they're going to start a certain distance away. Okay, let's jump to the code, and I will give you this code at the end. Okay, I'm going to put my constants here. MA is 0.1, MB is 0.3, B is 1. That's my force constant. What else do I have? I'll pick a position, but let's not worry about that. Let's just go ahead and make our spheres. So I'm going to say BA, it's a ball. Ball A is equal to a sphere. I'm going to put this one at the origin. Position, no, let's put it at a position vector negative 0.200, and it's a tennis ball, so it has a radius of, I'm just thinking in my head, let's say 0.05. And this one's going to be color equals color dot yellow. And make trail equals true. And then B is a sphere. Position equals vector 0.200. Radius equals 0.05. Color equals color dot cyan. And then make trail equals true. Okay, now I need their initial momentums. So I'm going to say BA dot P is equal to MA times vector. I said it was going at 0.2 meters per second, 0.200. And then BB dot P is, I'm going to say MB times vector 0, 0, 0. I just like to do it that way. And I know I'm going fast because I'm just excited. Okay, I don't even know if this is going to work. I've never actually done it this way. So, okay, so I have my initial positions. These are the initial positions. Those are the R vectors. I have the initial momentums. And I'm just going to let it run, right? I think I can go ahead and go. So let's just say t equals 0, dt equals 0.01. And I'm going to run it for 2 seconds. While t is less than 2, rate 100. So I want it to run in real time. So rate says don't do more than 100 calculations every 100 loops every second. With a time step of 0.01, this should take 2 seconds. Number one, I'm going to calculate R. So R is equal to, it's the vector from A to B. So it's going to be equal to B dot POS minus B A.POS. Case matters. You can't change the case. So that's BPBB.POS is RB. That's the vector position of that object. Okay, so that's my thing right there. Now I'm going to calculate F, and this is the force on B. It's going to be equal to B. I'm just going to use that number, but that's fine. B times R hat, which is norm R, right? So Python has a unit vector function built in. It's called norm, so you just do norm. And I need to divide by the magnitude of R, and then I'm going to cube that. And that's my vector force. Now I'm going to update the momentum of B. So B.P equals B.P plus F times dt. That's not so hard. Because that's the only force acting on it. Now I'm going to do the same thing for A. BA.P equals BA.P minus F times dt. Because remember, the force on A is opposite the force on B. I calculated the force on A, so I calculated the force on B. So the opposite force would be I just have to say negative. I don't have to recalculate the force. Now I'm going to update the position of B. B.POS, B.POS. So this up here, in case you haven't seen this, those two don't cancel because this is not an equal sign. Okay, it's an equal sign. It's not an algebraic equal sign. It's a make equal to sign. So I don't have to worry about indices and stuff. I can just change the value of the momentum and the position. Okay, back to the position. It's going to be B.P times dt divided by MB. BA.POS is equal to BA.POS plus BA. My letters are just bad choices today, but that's fine. You can't stop. Once you make bad choices, you have to stick with those bad choices forever. Okay. I don't know if this is going to... I didn't even test if they were looking good. I'm just going to run this. I don't know. If this works, I'll be very impressed. Okay. So, they moved apart. So I think what happened was my force is my B value is too large. And so it went boom, and they just pushed each other apart. So let's put this at 0.01 and see what happens. Okay, it's still kind of large. And they're starting pretty close together. So let's put this at 0.5, negative 0.5, and run that and see what happens. Okay, it's working. It's just not working as well as I wanted it to. I'm going to make this even smaller. It's not going very fast. Let's run this let's just increase this. See, that's the great thing about Python. We can just change these numbers around. Okay, and it stopped. Let's just increase the speed and the time. Okay. Yes. 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 Like it. So they didn't touch, right? So what happened was, as it got really close, the closer they got, the greater the force pushing them apart was, and eventually it stopped mass A and started B moving, and so it looks like a collision, even though they didn't touch. Let's plot the momentum as a function of time to see if momentum was conserved. So I'm going to go up here, I'm going to make a graph. G1 equals graph. Title equals momentum stuff. You got to capitalize that. Momentum stuff. X title is equal to time. And the Y title is equal to momentum in kilogram meters per second. I like to put the units. And then let's put a width of 400. I should make that a little bit bigger. And a height of 200. And then I'm going to make my graph FA equals G curve. Color equals color dot. I would make it the same color as the objects, but it won't show up. Color equals color dot blue. And then I guess I should put that label. And this will be equal to A. FB equals G curve. Color equals color dot red label equals B. So down here, I'm going to plot that stuff. So let's put it right before the time. So FA dot plot, I want to plot time and the X value of the momentum. So be BA dot P dot X. That's the X component of the momentum of object A. And then same thing for FB dot plot, TBB dot P dot X. And up here, let's do one more graph. FT equals G curve, color equals color dot purple. I've been liking purple lately. And then label equals total. Nope. Yep. And then, so down here, let's calculate the total momentum. I'm just going to plot it over here. It's going to be equal to, oops, FT. Did I call that? Ooh, look at that. I got to have these as FA, FB, FT dot plot, T. I'm going to write this actually as B, I think I can do this, BA dot P plus B dot P, and then dot X. I wonder if that works, because I want to add them and then take the X component. I could do it the other way, but I just like this better. Let's see what happens. I don't know. I've never done that before. I think it should work. I didn't even save this. New conservation of momentum. I will give you the code, because I'm a code giver. Okay, let's run it. Oh, so it did not like that. It did not like that. That's fine. Okay, so, okay, what? Fine, go away. So I'm going to say dot X, there. No. FT dot plot is not a function. Oh, I misspelled it. Oh, so maybe I was right the last time. That's fine. I just misspelled it. Go away. P plot. That was a problem. Okay, so here's the momentum. So you'll notice that object A, the momentum is decreasing, and then it goes back to negative. B was 0, and then it increased, but the total was constant. This is a win. This is a total win. But wait, I'm not done. Because I told you I was going to show you something awesome, and I have. But now I'm going to show you something awesomer. So awesome that you won't be able to believe how awesome this is. Let's go to edit. I'm going to change one thing. You could change the masses, and you should. You could change the constant of how much force there is between them. You should change all that. But I'm going to start A, instead of having them crash like this, I'm going to have A shifted up a little bit. And actually, I guess this would be A. I'm looking at my screen. A shifted up a little bit. So I'm going to have its position at, let's say, and it doesn't matter what it is, let's say but 0.01. So it's not directly head on. So when they get close, the force is going to push it up at an angle because that's the way R is. And let's see what happens. Look at that. 2D collision. Okay, let's increase that. Technically, it's called the impact parameter. Let's make that something large. I told you that was awesome. This is in 3D too. So, and let's look down here. Is momentum conserved? Momentum is still conserved. I'm plotting momentum in the X direction. We can actually do this in the Y direction too. Let's go up here and change these to Y. I can't plot the total momentum because that's a vector. So let's change all these to Y, 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 and then let's run this. And oh, we already saw that. Let's look at this. So there you go. So they both start off with 0 Y momentum, but then as they collide, They move apart. They don't have the same velocity in the y direction because they have different masses, but they have equal and opposite momentums, so that the total y momentum is 0. What if I can even make them miss but hit, right? So let's increase this to 0.15 in the y direction. So it should miss it, but it's not going to miss it because the force between them is still pushing on them. So it still has a collision, okay? And this is what would happen with gravity. You can have gravitational collisions where they don't touch. This happens with the Rutherford experiment where he shot alpha particles at gold foil. Same kind of thing happens. But there you go. Momentum is conserved. And yes, that is awesome. So this is not elastic or inelastic. I mean, it's technically... It might not even be elastic because I think you have some potential energy terms in there. But it doesn't matter. It's a collision. And momentum is conserved in a collision if there are no external forces. Doesn't matter about elastic or inelastic. Okay. But this is a simple collision. You can change. So what you should do is go over here. Try changing these masses. Try changing the initial positions. Try changing the initial velocities. That's all fun stuff. Try changing the way force is calculated. I did 1 over r cubed. What about 1 over r to the 4th? What about r? If you do r, well, you still want to, yeah, you can do that. You can change it up. Do what you want. Now, if you do r, then that force is greater the further apart they are, and so that's a little weird, but you can still do it. Okay, so I'm going to give you this code down below. Hope you enjoyed that. I had fun. You know I had fun. Did I save it?